So our next speaker is going to be Kevin Mizes, and his talk has the title Identical Encoding of Flexible and Automatic Motor Sequences in the Dorsal Lateral Striatum.
Okay, my own adapter works. Cool, so thanks for the invitation to speak here. So an amazing feat of the brain is its ability to control such a large set of complicated and diverse behaviors. One way in which it can do this is through flexibly reorganizing existing basic movements in a near infinite number of ways. This can be exemplified by the key presses of the concert pianist. When provided with sheet music, she can perform any number of sonatas or etudes. However, to prepare for a concert, where precision is of essence, she extensively practices a single piece over and over again until overtrained into an automatic sequence. Although these movements are made from the same basic elements, they feel qualitatively different to us. For example, the pianist, who if she messes up in the middle of the automatic performance, might find it harder to restart right there and easier to start at the beginning. You yourself may experience this on a more ubiquitous task, typing in a password. At least when I'm doing this, if I mess up halfway through my password, I find it easier just to delete the entire thing and start over than fix the mistake in the middle. Whereas if I'm performing a flexible typing task, such as entering a CAPTCHA to prove I'm not a robot, it's much easier to fix mistakes in the middle. And so in general, we believe these flexible and automatic sequences engage different neural circuits. However, the mechanisms underlying this are not well understood. And here to test this in a principled way, we need a task in which the same sequence is performed in both a flexible and automatic way. We also need a model that is amenable to detailed circuit dissections. And so to do this, we've been developing taking inspiration from the pianist, we've been developing a piano playing task for rats. In this task, rats can press one of 3 discrete levers akin to piano keys. The levers are cued with a light above the lever, just like sheet music, and rats can quickly learn to associate a lever press with this visual cue. After learning this association, we can sequentially present the visual cues so that the rats perform a sequence of 3 lever presses akin to playing a short little piece. Rats can perform this movement in both a flexible and an automatic way. In one session, rats flexibly perform different cued sequences, as just described, that continually change throughout the session. On a completely separate session, a single sequence is chosen and fixed. This sequence is overtrained for the rest of the rat's life. They perform this night after night for thousands and thousands of trials until done automatically, no longer reliant on the cues. As one might expect, performance in this overtrained context is both on average faster and more precise than performance in the cued context. But qualitatively, if you watch the rat doing this, the movements look similar. So here's an example. Here's an example on the left of an animal performing this task driven by those green LEDs in a cued performance. And on the right is a video of the animal doing the same task, the same sequence, but now in the automatic context. And so, whether she's following these green cues or doing it automatically from memory, qualitatively, the movements look similar. We can quantify this by tracking the forelimb position over many trials. So here is a handful of trajectories, which I've aligned to the lever taps for the cued sequence right, left, center. And the Y position is just the location on the camera. As you can see, the animal uses a similar trajectory across different trials. We can do this for the same sequence, but in the overtrained context. Overlaying the two reveals the animal uses a similar trajectory across both the contexts, which we can further quantify by looking at the correlation of individual trajectories within the overtrained context, within the cued context, and across the two contexts. So now that we have a task in which the same sequence is performed in both a flexible and automatic way, we can begin to interrogate how the motor system differentiates these types of movements at a neuronal level. And so the motor system is large and dispersed throughout the entire brain. In general, we believe these different regions control for different aspects of movement. In particular, flexible and automatic sequences are thought to be differentiated in the basal ganglia, more specifically, the sensory motor arm of the basal ganglia, the dorsal lateral striatum. The dorsal lateral striatum, or DLS, has long been implicated in controlling aspects of automatic movements. Lesions to this area have prevented the formation and execution of automatic sequences, and recordings from this area have revealed neural activity that reflects consolidated movements. However, exactly how this region generalizes and differentiates these automatic movements to flexible ones has not been directly tested. And so here we can do this in our task just by using electrophysiological techniques to record from the DLS while animals perform these sequences. And so I'll show you now a video of 4 trials of the rat doing the sequence right, left, center in the cued context. Simultaneously, I'll show you tracked forelimb and the spikes from a single unit in the DLS. And as you can see, as the animal does these trials, this unit appears to preferentially fire between the second and the third lever press, suggesting it is sensitive to some aspect of this sequence. However, we're curious how this unit would respond when the animal's doing this movement but overtrained automatically. And if this unit were to differentiate these types of movements, we might expect activity to differ. So we can track this unit over time, return to the animal in the night when she's doing the same sequence automatically, and watch what this unit does. And as you can see, this unit still prefers to fire between the second and third lever press, suggesting, well, it's maintaining this movement-sensitive aspect, but it really seems to be insensitive to the context. And so we can zoom out and look at more trials from this unit and see this persists, and we can see this as well across other units. I found that while they appear to be sensitive to some aspect of the movement, they are insensitive to the flexible or automatic context. And so let's look at more than 3 units. So here's a heat map of trial average neural activity over 220 units. The x-axis is time in the sequence, which I've warped and aligned to the lever taps. The y-axis are individual units, and the color map is the z-scored firing rate. I've sorted these units based on their peak firing time in the sequence, which reveals that there's different movement-related aspects in this population of neural activity. If we look at these exact same units in this exact same sorted order while the animal does the sequence in the overtrained context, a very similar pattern emerges, really suggesting the DLS is actually not representing cued and overtrained sequences differently. And we can see this is consistent in the low-dimensional representation of the neural activity as well. I'll just show you how that evolves along the first 2 principal components in the cued and overtrained movements, and you can see they follow each other quite closely. So contrary to our expectations, it seems like flexible and automatic movements are represented very similarly in the DLS, but however, we still see a lot of movement-related activity. And so what aspects of the behavior are actually being encoded here? One possibility is that the DLS is encoding low-level information about the movement, just such as the kinematics, just tracking the basic movement kinematics. Another possibility is that the DLS is encoding high-level movement information, such as the specific action the animal's doing, like which lever it's pressing, or where in the sequence it is, what order of the levers it's in. And in general, past work in the field has found evidence for both these things in conflicting and sometimes contradictory studies. But this past research generally looks at these aspects of behavior in single inflexible automatic sequences, where it can be difficult to dissociate low-level from high-level information. In our case, we can look at our flexible sequences to more easily dissociate low-level from high-level aspects of movement. So to do that, let's just go back and look at the neural activity. So here, again, is the heat map over the cued sequence, right, left, center. Again, the color map is the z-scored firing rate of the units. And so if the DLS was representing high-level movement information, we might expect activity around each lever press to look different. This would be because different subpopulations would be encoding particular levers or particular phases in the sequence, and they'd all be different here. But if you look at each lever tap, you can see a set of neurons that fire every single time the lever is pressed, independent of which lever the animal's pressing or where in the sequence it is. We can see this in the low-dimensional representation of the neural activity too. I'll just drop a red dot every time the rat presses the lever, and you can see it it ends up in roughly the same space, suggesting DLS is not differentiating between these lever presses. This is consistent over not just this flexible sequence, but over 10 different flexible sequences I'll show you here, plotting how this activity evolves together. And anytime the animal presses the lever, now independent of the sequence, activity roughly returns to the same state, suggesting DLS is representing taps, all the taps the same, consistent with a low-level kinematic role. Further evidence for this low-level kinematic role comes from the activity between the taps as well. As you may have noticed, activity between the taps takes one of two paths, either horizontally along the first principal component or looping up along the third. And further investigation into this reveals they're just encoding which direction the rat's moving. So, for example, take the sequence center, right, left. We can just represent this as which direction the animal is moving, starting off from the center to the right, which is a rightward movement. Activity will follow this first path. Then the animal will move to the left, going from the right lever to the left lever, and activity will follow this other path. And so we can look across, again, all our flexibly cued sequences and vectorize it as right movements, left movements. And anytime the animal moves to the right, activity all follows this lower path. And anytime the animal is moving to the left, activity follows this upper path. And so in summary, we found flexible and automatic sequences were represented very similarly in the dorsolateral striatum. In addition to this, when we tried to see what aspects of the movement were being encoded here, we found that the DLS what we found was much more consistent with a low-level kinematic role, basically representing the taps and the movement direction, independent of the specific levers or where in the sequence the animal was. And so even though the animal's been performing one of these sequences automatically for thousands and thousands of trials, the DLS never develops a consolidated representation beyond this basic kinematic, a function of its basic kinematic features. And since we believe the motor system must be distinguishing these flexible and automatic sequences somewhere, we suspect it's elsewhere in the motor system, higher order area like the motor cortex, which will be the basis of future research. And before I finish, I'd just like to thank my lab, Bence Ölveczky, and everyone there jumping happily here. They've been tremendous help and will continue to be so. And thank you for your attention.
Thank you, Kevin. Are there any questions?
Great talk. Just a quick question. In your PCA plot, the two axes are PC1 and 3.
Yeah.
I'm just curious about PC2 and also other PCs.
PC2 doesn't differentiate the movement direction.
Okay.
It's representing other stuff. And the other PCs, it's mixed. Some are the same, and there are some other principal components that also differentiate the movement direction.
I see. Thank you.
Okay, if there are no further questions, thank you, Kevin, again. Our next speaker is going to be Sima Mofakham, and her talk has the title, one second, Exploring the Hidden State of Coma.